watching session number 3 of the chapter Biomolecules. In the previous session, I discussed about monosaccharides, in particular the concepts related to glucose and fructose I discussed. In this session, I am going to talk about disaccharides, polysaccharides and proteins. Disaccharide belongs to carbohydrates, we know that. On the basis of hydrolysis, carbohydrates are classified into 3 types. First one is monosaccharide, second one is oligosaccharide, third one is polysaccharide. Carbohydrates which gives 2 to 10 monosaccharides on hydrolysis, we call it as oligosaccharide. If any carbohydrate, if it gives only 2 monosaccharides, that may be same or different by the action of either enzymes or dilute acids, and these carbohydrates we call it as disaccharides. Remember, if you have disaccharide and on hydrolysis you are going to get 2 monosaccharides. And if you observe the structure of disaccharide, we have 2 units of monosaccharides, and the examples for disaccharides are maltose, lactose and one more is sucrose. So now we are going to draw the Haworth structure of maltose, lactose and sucrose. We know that one Haworth structure is cyclic structure, and we have drawn the Haworth structure of glucose as well as fructose. Similarly, I am going to draw the Haworth structure of maltose, lactose and sucrose. Remember, these 3 examples what I considered, maltose, lactose and sucrose, belongs to a category of carbohydrates. We call it as disaccharide, isn't it? Then the Haworth structure of these disaccharides consist of 2 monosaccharides, and these 2 monosaccharides are joined, and 2 monosaccharides are joined through oxygen atom, and we have a kind of linkage or joining or bond you can say, and that linkage that joins between 2 monosaccharides through oxygen, we have a name for that we call it as glycosidic linkage. I repeat the word, glycosidic linkage. And now you need to remember, in carbohydrates, especially in case of oligosaccharide and polysaccharide, the kind of bond present or the kind of intermediate chemical bond present between the monosaccharide units is glycosidic linkage. The linkage between 2 monosaccharide units through oxygen atom, we call it as glycosidic linkage. So now I am going to draw the Haworth structure of the first disaccharide what I am going to consider, that is maltose. So now observe here, I am going to draw the Haworth structure of maltose, and we know that one maltose belongs to disaccharide, and one can easily guess this maltose Haworth structure has 2 monosaccharides. And before drawing the structure of maltose Haworth structure, you should know, when you consider maltose and on hydrolysis, what are the products we are going to get, what are the monosaccharide products we are going to get, you should know for that. And what kind of monosaccharide units we are going to get, I am going to write here. The first one is alpha D glucose, and one more is, that is also alpha D glucose. So try to remember these monosaccharides we are going to get after hydrolysis of maltose, and the 2 monosaccharides are alpha D glucose and alpha D glucose. And we know what actually alpha stands for and what actually D stands for. Alpha is nothing but, on anomeric carbon we have OH group on right side in the structure of glucose. D stands for, on asymmetric carbon of glucose, in particular carbon number 5, we have OH on the right side. Therefore we have alpha D glucose, and glucose, these two are plus glucose, because this substance rotates plane polarized light towards right side. So now what I am supposed to do is, I am going to draw the Haber structure of glucose, and one more monosaccharide is, that is also alpha D glucose, and these two glucose I am going to draw, and I am going to join these two monosaccharides using glycosidic linkage. Glycosidic linkage, two monosaccharides are joined through oxygen atom. We call it as a glycosidic linkage here. So just observe carefully how I am going to draw the Haber structure of maltose. Important for the examination, for 2 marks these structures are. Okay, so now I am going to draw the first monosaccharide, that is alpha D plus glucose. So observe here, we have glucose, and from the previous session we know that one glucose has pyranose ring, isn't it? Whereas fructose has furanose ring. Pyranose ring, 6-membered ring with oxygen. Furanose ring, 5-membered ring with oxygen. So since I have glucose, I have to draw the 6-membered cyclic ring with oxygen. So how I am going to draw here? Just see. We know that one. We have oxygen here. So this is the skeleton, or you can say the pyranose ring structure what I have. And what is the next thing we need to do? We need to draw the vertical lines at the corners, and these represents the chemical bonds, as I told you. And these are the groups has to be placed above the plane, and the remaining are the groups has to be placed below the plane. Numbering is also as important. So we know that one, in glucose oxygen is in between carbon number 1 and 5. Therefore you should number in such a way that this oxygen should be in between number 1 and 5. For that one I should consider this carbon as 1. This is carbon number 2, carbon number 3, carbon number 4, carbon number 5. As I told you, carbon number 6 will be always above the group. So this is the skeleton what I have drawn for alpha D glucose here. So now you should be quite good in Fischer structure of glucose, and how we transformed that Fischer structure of glucose into anomeric form of glucose, alpha D glucose and beta D glucose. As I told you already, in the Fischer structure or open chain structure of glucose, alpha stands for on anomeric carbon we have OH on the right side. And the rule we know, the groups which are present on the right side has to be placed below the plane in the Haber structure. Okay, so since I am going to draw the structure of alpha, so you need to imagine. Okay, so we have alpha means OH we have in the right side, and what I should do, I have to place OH below the group, and one more will be H, that is above the group. Okay, so without drawing the Fischer structure, you should be able to draw the Haber structure directly. Okay, so now what I am going to do next is, which one is a bit confusing or which one is a bit change, I am going to draw that first. We know that one on carbon number 3 in Fischer structure, H is on the right side, isn't it? So on this carbon number 3, since H is on the right side, so H I place below and OH I place above, right? And remaining the configuration at 2 and 4 are exactly opposite of 3. Therefore OH below and H above. Here OH below and H above I am going to draw. And carbon number 5, CH2OH is always above the plane, and one more is H we are supposed to write here. So this is the Haber structure of alpha D plus glucose. So this is how you need to recall what would be the Fischer structure of alpha D glucose, and based on that you need to draw the Haber structure. So skeleton we need to draw, vertical lines we need to draw, numbering is also as important, and we need to write the correct substituents by checking whether it is below the plane or above the plane. So this is one monosaccharide what we have drawn, and that is for alpha D glucose. Remember, in a maltose, as I told you, we have a 2 monosaccharide, and one more monosaccharide is the same. What is that? Alpha D glucose. So here I need to draw one more alpha D glucose here. And now since I explained this already, the first one, and it will be easy for you to draw the second one. So now just see how I am going to draw the one more structure of alpha D glucose. So first I am going to draw the skeleton, and in the examination also the Harvard structure should be very neat. Vertical lines, and the groups are visible, that you should take care of that one. Numbering will start from here: 1, 2, 3, 4, 5 and 6. Alpha D glucose, OH below, H above. On carbon number 3, H below, OH above. 2, 4 is that of opposite configuration, OH and H, and here OH and H, and CH to OH is always above the group and H is always below the group. So this is how you need to remember the Harvard structure of alpha D glucose. So now I have drawn just the 2 structures, that is alpha D glucose, and one more is also alpha D glucose. So what you need to do, as I told you already, these monosaccharides are linked by glycosidic linkage through oxygen atom. And remember, glycosidic linkage is formed by elimination of water. You need to eliminate the water here. So now if you observe the configuration at C1, we have OH here, and carbon number C4 we have OH here. So OH we have, and from here elimination of water takes place. So H2O is going to be eliminated, isn't it? So if H2 is going to be eliminated, we are left with oxygen atom. So how we are supposed to do? So I am going to link with what actually? Oxygen. So this is how you need to mention the glycosidic linkage in between the 2 monosaccharides of alpha D glucose, and that is what actually the glycosidic linkage. And the what kind of glycosidic linkage is present, you need to remember here. So if you observe the first monosaccharide, and here we have, this is carbon number 1, this position is carbon number 1, and this position is what actually? Carbon number 4 here. So the glycosidic linkage present in maltose is, I am going to write here, that is C1C4 glycosidic linkage. You need to remember that. The glycosidic linkage present in maltose is C1C4, and one more representation we have. I can write like this also: alpha in bracket 1, 4. What this alpha stands for? Both monosaccharides are alpha configuration only. What are these? 1, 4. That indicates carbon number 1 of one monosaccharide is going to link with the carbon number 4 of one more monosaccharide through oxygen atom. That is nothing but C1C4. So the glycosidic linkage present in maltose is C1 and C4 here, and that is the complete Harvard structure of a maltose. You need to remember that one, and for that you need to know the products what we are going to get after hydrolysis of maltose, and the products are alpha D glucose and alpha D glucose. And remember that the glycosidic linkage present in maltose is C1C4 glycosidic linkage. And you just recall the previous concept of what I told while explaining the the classification of carbohydrates. The one more classification I told you: reducing sugars and non-reducing sugars. Reducing sugars, the sugars which reduces Tollens reagent and filling solution, we call it as a reducing sugar, and the sugars which won't reduces Tollens reagent and filling solution, that we call it as non-reducing sugars. Remember, maltose belongs to reducing sugar, since there is a presence of a free aldehydic or ketone group. So here we have a free aldehydic group. So because of presence of a free aldehydic group in maltose, so maltose belongs to a category that we call it as a reducing sugar. That is about the first disaccharide, that is maltose. Second example for disaccharide I am going to discuss now, that is lactose. Lactose is present in milk. We call it as milk sugar. So now we'll see what would be the Harvard structure of lactose, milk sugar. For that one, as I mentioned in the previous case also, we need to know what are the monosaccharides we get after hydrolysis of lactose. That is beta D galactose is the one monosaccharide, and one more will be beta D glucose. Beta D glucose. So when lactose undergoes hydrolysis, we get two monosaccharides. The one is beta D galactose and one more is beta D glucose. So now I hope you can draw the Harvard structure of beta D glucose. Beta on anomeric carbon, OH is on the left side. Means in the Harvard structure we need to write OH above the plane, isn't it? But this is a new one for us, that is beta D galactose. Galactose, we have not discussed about that. So galactose is also one example for monosaccharide. And what is the change we are going to get in galactose with respect to glucose is change in configuration. Change in configuration at carbon number 4. Galactose structure will be as same as glucose, but the change what we are going to see is at carbon number 4 only. On carbon number 4, we have OH on the right side, H on the left side in case of glucose, but while drawing this Harvard structure of galactose, you need to interchange the OH and H. So that's why I have written here change in configuration of C4 occurs in case of galactose and structure is as same as the glucose here. So now I am going to draw what actually beta D galactose. So just observe here how I am going to draw the Harvard structure of that. So that is also the 6-membered ring with oxygen. So I am going to draw the cyclic structure, that is a pyranose ring. You need to use scale and pencil and you need to draw in a very neat manner in your notes. And the vertical columns I am supposed to draw here, that indicates the bond, and the numbering starts from here: carbon number 1, carbon number 2, carbon number 3, carbon number 4, this is 5, 6 will be above the plane. Since we have a beta, so what actually beta stands for? Anomeric carbon, OH is on the left side and the group which is present on the left side has to be placed above, therefore OH I will write and H I am going to write here. Carbon number 3, we have H below, OH above. Okay, but since I am going to talk about galactose and I told you that one structure is as same as glucose, but the configuration at carbon number 4 is different, and configuration at carbon number 4 in glucose, below the plane you get OH, above the plane you get H, but since this is galactose and above the plane I should write OH and below the plane I should write H. So this is a change in configuration at C4 we are going to get in case of what actually the galactose. And carbon number 2 is the same, that we know, OH and H, and carbon number 6 is always above the plane, CH2OH and H, and that is the structure of beta D galactose. This is as same as beta D glucose, and the change in configuration we have at C4, that is the change what we are going to see while drawing the structure of galactose. So one more monosaccharide what we have is beta D glucose. So we will draw that one, beta D glucose. So how would be the structure of beta D glucose? So since we have glucose again, and we need to draw the 6-membered ring with oxygen, and here I have the structure of that. So skeleton I need to draw first, right, and next the vertical lines I need to draw, and after that the next step is we need to give numbers for that one: carbon number 1, carbon number 2, 3, 4, 5 and 6, right. Beta D glucose, beta OH is present on left side of anomeric carbon, and here OH should be above and H should be below. Carbon number 3, H is below, OH is above. Carbon number 2 and 4, that is opposite of the configuration at 3, that is OH below and H above. CH2OH is always above the plane and H is below the plane. So this is beta D galactose and this is beta D glucose. And we need to join these two through oxygen atom, and that kind of linkage or bonding we call it as glycosidic linkage. And I explained that glycosidic linkage is formed by elimination of water in between combining monosaccharides. And if you observe the carbon number 1 of this monosaccharide and carbon number 4 of this monosaccharide, OH we have above the plane, OH we have below the plane. Therefore OH in between these two, H2O is going to be eliminated, and we know that when we are left with the oxygen atom. And how we need to draw that? So this is how you are supposed to draw the glycosidic linkage. In the previous case maltose, we have OH here, we eliminated water and we have represented O here. But in this case of lactose, OH we have above and OH we have below. Therefore you need to join like this, and that we call it as what actually the glycosidic linkage, and this is the Harvard structure of lactose. Now I hope you can guess and you try to answer me, what kind of glycosidic linkage present in a lactose? Glycosidic linkage present in lactose is, you need to see to which carbon it is going to be joined. Carbon number 1 of beta D galactose, carbon number 4 of beta D glucose, and the glycosidic linkage present is C1C4 glycosidic linkage, as same as the previous one maltose. And one more way you can represent, I can write beta 1, 4. Previous one maltose, it was alpha 1, 4. Beta, why beta? Both the monosaccharides are with the beta configuration, therefore beta 1, 4, and usually we prefer this method, C1C4 glycosidic linkage we have in case of lactose. So lactose, the glycosidic linkage is a C1C4. And this also belongs to a category that is the reducing sugar, since this reduces Tollens reagent and failing solution, since presence of free aldehyde group in the structure of lactose. That is about the Harvard structure of a second disaccharide, that is lactose. Now we'll see the third example for disaccharide, that is sucrose. So now I am going to draw the Harvard structure of sucrose. We don't have a single kind of representation for mentioning the Harvard structure of sucrose. Here I am going to write the Harvard structure of sucrose as per NCERT textbook. Sucrose is the third example for disaccharide, and when sucrose undergoes hydrolysis, and the monosaccharides what we get are, one is alpha D glucose and one more is beta D fructose. See here, on hydrolysis sucrose yields alpha D glucose and beta D glucose, beta D fructose. We need to draw Harvard structure of glucose, we need to draw Harvard structure of fructose, we need to link through glycosidic linkage. That would be the Harvard structure of sucrose here. Remember, we have glucose, pyranose ring we need to draw, but here we have fructose, furanose ring we need to draw. 5-member cyclic ring with oxygen we need to draw in case of fructose here. So this is alpha, the first monosaccharide, and the second one is beta. You need to take care of that. And now I am going to draw about the Harvard structure of alpha D glucose. And now just to see how I am going to draw the Harvard structure of alpha D glucose. This is the pyranose ring. Therefore 6-membered ring with oxygen I am supposed to draw. And now I hope you are perfect in drawing the Harvard structure of alpha D glucose. Vertical lines I am going to mention at the position of carbons. Numbering is also important one, and we know how to number the pyranose ring. Alpha D glucose OH is present on right side of anomeric carbon, and we need to place below the plane. So OH and H. Carbon number 3 hydrogen is below, OH is above. 2 and 4 is opposite configuration with respect to carbon number 3, OH and H, and CH2OH is always above the plane and H is below the plane. That's it. So this is alpha D glucose. We'll see beta D fructose. Remember I told you fructose we have furanose ring. So just to see, furanose ring we have. So furanose, and I hope you remember how the furanose ring looks like, and 5-membered ring you need to consider, and this is how the furanose ring looks like. And now we need to consider the vertical columns, right? And the groups which are present above the plane, below the plane you need to draw, and we need to link through oxygen atom, and that would be the structure of sucrose. So here, before attempting the placement of groups and glycosidic linkage, and here let me explain the same concept because the fructose is completely different when compared to the glucose, so it may confuse you. So I am going to explain that again, how actually the fructose structure should be drawn. So this is actually the furanose ring what you are supposed to draw, and now I am going to draw the structure of beta D fructose. See here, beta D fructose. If you observe the structure of fructose, we know that one, the oxygen is present in between carbon number 2 and carbon number 4. So therefore, the numbering I start from here, carbon number 2, 3, 4 and 5 we have. Sorry, 2 and 5, it is in between 2 and 5. Since we have beta, OH is present on left side. Left side means I need to draw OH above. And do you remember what would be the another group in case of fructose? That is CH2OH. Carbon number 3, H is below, OH is above. Carbon number 4, opposite configuration, OH and H. Carbon number 5, CH2OH is above and H is below. This is carbon number 6 and this is carbon number 1 we have. So structure what I have drawn here, that is a beta D fructose here. For that you should know what would be the Fischer structure of fructose, that I explained in the previous session. And now we need to draw the same structure here. But before I will mention that the glycosidic linkage present in sucrose is C1C2 glycosidic linkage. Know that one. The glycosidic linkage present in sucrose is C1C2. So we have carbon number 1 and we have carbon number 2 of the fructose. And if I place the same structure, if I draw the same structure here, and this is carbon number 5 actually, this is carbon number 5, and where is the position of carbon number 2 in fructose? This is the position of carbon number 2. But the glycosidic linkage is carbon number 1 and 2. 1 we have here and 2 we have here, and it is difficult for us to join through oxygen, isn't it? So to remove this problem, and what I am supposed to do is, I will draw the same structure of fructose, but inverted structure I am going to draw here. Opposite the groups we have to place here. Okay, and for that one, what I am supposed to do here is, just to see, the numbering is 1, 2, 3, 4, 5, 6. If I invert the structure, here, the structure I am going to place over here like this. Okay, and this would be carbon number 1. Carbon number 2, carbon number 3, carbon number 4, carbon number 5, and this is carbon number 6. Just see, the same structure I have inverted. And I told you the reason also why I have to consider, because if you invert the structure, and now see we have carbon number 1 and carbon number 2, and the glycosidic linkage is C1C2, we know that. Okay, so for that reason I am going to invert the structure. One more very important thing you try to know, if you invert the structure and if you draw the opposite structure of that one, the groups also interchanges. The groups which are placed below will come above, the groups which are placed above will come below. So on carbon number 2, okay, so we have CH2OH here, and opposite will be, what is that, OH. Carbon number 3, we have H below, isn't it? So H we get above and OH we get below. Carbon number 4, see there, we have OH below, H above. I will take inversion of that one. So OH above and H below. Carbon number 5, I will take the inverse, that is CH and CH2OH we have, and that is the beta defructose. But this is not as same what we have drawn here. I have taken the opposite structure of that one, since I need the glycosidic linkage C1 and C2, and now we know that one we have OH here and OH here. H2O is going to be eliminated, and therefore the glycosidic linkage through oxygen I need to link, and that we call it as the C1 C2 glycosidic linkage, and that is the Harvard structure of sucrose. You just recall how the procedure has to be followed. And if you feel difficulty in drawing the Harvard structure of maltose, lactose and sucrose, and I suggest you to watch the previous session number 2 of biomolecules again, because that is the basic. We have discussed only the single monosaccharide Harvard structure and rules, and based on that, and this session 3 depends on. Watch it again if you have a problem in drawing the Harvard structure. And glycosidic linkage in sucrose is C1C2. And remember, this belongs to non-reducing sugars, because we don't have free ketonic group as well as free aldehydic group. So based on this, I can say sucrose belongs to non-reducing sugar, and I have discussed the Harvard structure of maltose, lactose and sucrose. Maltose, lactose, the glycosidic linkage is C1C2. Sucrose glycosidic linkage is C1 and C2 here. That is all about the concepts related to disaccharides. Now I am going to talk about polysaccharides. Carbohydrates which gives large number of monosaccharides on hydrolysis, we call it as polysaccharides. Polysaccharides are known as non-sugars, isn't it? The reason behind that is polysaccharides won't provide sweetening effect, and examples for polysaccharides are starch, cellulose and glycogen. So let me explain the concept related to starch, cellulose and glycogen, which are the examples for polysaccharides. Now I am going to talk about the first example of polysaccharide, that is starch. So starch is the best example for polysaccharide, and we know that when starch undergoes hydrolysis, we get a large number of monosaccharide, and the monosaccharide is glucose. Remember that carbohydrates are stored in the plant body is in the form of starch, and therefore starch is also called plant carbohydrate also. That acts as the storage for the carbohydrates that are going to be utilized by plants at the time of need. So therefore the key point what I am going to write is carbohydrate, or the polysaccharide you can say actually, carbohydrate stored in plants is in the form of starch. And the monosaccharide what we get is that we know alpha D glucose is the monosaccharide. Alpha D glucose will join with one more alpha D glucose through glycosidic linkage, and you are going to get a structure of starch. But starch contains two different components. Remember that. One is amylose and one more is amylopectin. I am going to write here. The two components of starch are, one is amylose, the one component, the constituent you can say, and one more is amylopectin. Amylopectin. So these are the components of starch. So amylose and amylopectin constitutes, and we are going to get the polysaccharide, that is starch. And now what are the concepts related to amylose we will see, as well as amylopectin, so that constitute entire the polysaccharide that will be starch. Remember that when you compare amylose and amylopectin, amylose is water soluble, know that, whereas amylopectin is water insoluble. So based on this property, we can differentiate which component is amylose and which component is amylopectin. Amylose is water soluble, whereas amylopectin is water insoluble. Amylose is linear polymer, whereas amylopectin is a branched polymer. You try to know that one. Linear polymer. The alpha D glucose are arranged in long and straight chain manner, and that we call it as linear polymer. Whereas in case of amylopectin, of course we have a long and straight chain polymer of alpha D glucose. Apart from that, we have branches, therefore that belongs to branched polymer. What kind of glycosidic linkage present in between these two, we'll see. In case of amylose, we have C1-C4 glycosidic linkage. In case of amylopectin, we have C1-C4 as well as C1-C6 glycosidic linkage. So this is about the glycosidic linkage present in amylose and amylopectin. As I told you already, glycosidic linkage is present in carbohydrates. C1-C4 glycosidic linkage, what is the meaning of that? The oxygen atom is linked with carbon number 1 of one monosaccharide and carbon number 4 of one more monosaccharide, and that we call it as C1-C4 glycosidic linkage, which is present in amylose. Whereas in case of amylopectin, we have two different kind of glycosidic linkage, C1-C4 and C1-C6 glycosidic linkage. And if you consider the proportion of these two, 50 to 20% of amylose will be present in starch, whereas 80 to 85% of constituent present in case of amylopectin. 50 to 20 and 80 to 85 will be the proportion of amylose and amylopectin in the structure of starch, and that is about the first polysaccharide, that is starch. The second one we will see. The second polysaccharide what I am going to talk about is cellulose, the known naturally occurring carbohydrate. Okay, and the cellulose, as you know, the plant cell wall is made up of cellulose. Cellulose is the most abundant polysaccharide present in plant body. You just try to know that one. Cellulose is the most abundant polysaccharide present in the plant body, and the glycosidic linkage and the monosaccharide will see. The monosaccharide will be beta D glucose. So beta D glucose is the monosaccharide present in a cellulose, and the glycosidic linkage present is the C1-C4 glycosidic linkage we are going to get in the polysaccharide structure, that is cellulose. Try to know that one. The cellulose is the most abundant polysaccharide present in plant kingdom, you can say. One more example, as I told you that one, that is glycogen. So glycogen belongs to polysaccharide again. Try to know that one. Glycogen, we have one more name, and that we call it as animal starch. So try to know, glycogen is called animal starch. What is the reason behind that? We know that one, starch is present in a plant body, isn't it? And a kind of same polysaccharide that is present in animal body, and that is glycogen. Therefore glycogen is called animal starch. Or I can say, in animal body the carbohydrates are stored in the form of glycogen. So what I am going to write here is polysaccharide or carbohydrate. Carbohydrate stored in animal body, in animals, and that kind of polysaccharide, that is nothing but glycogen. So try to know that one. Carbohydrates stored in a plant body is in the form of starch. Carbohydrates stored in animal body is in the form of glycogen. Polysaccharide actually, and at the time of need, that glycogen is going to be converted into glucose, and that provides energy later after the reaction. So carbohydrate stored in animal body, and that we call it as glycogen, and the one more name is animal starch. Why it is called animal starch? And the reason behind that I told you. One more reason I can say, and if you just look over the structure of glycogen, that constituent is as same as amylose and amylopectin. These are the constituents of starch actually. So that we have animal starch. And what kind of monosaccharide we have? We have alpha D glucose monosaccharide here, and the kind of glycosidic linkage will be C1C4 glycosidic linkage, and one more will be C1C6 glycosidic linkage present in glycogen. So these are the examples for polysaccharide. The first one is starch and cellulose and glycogen. And this is all about the monosaccharides, disaccharides and polysaccharides. Then what are the importance of carbohydrates? Remember, carbohydrate is the main source of energy. You just try to know that one. Carbohydrate is the main source of energy, because at the last of the reaction we get monosaccharides, usually glucose, and that provides energy to do work. So carbohydrates are the main source of energy. Since the cellulose, as I discussed, that is the main component present in cell wall of plant cell, and cellulose, or you can say in general polysaccharides or carbohydrates, that provides the main physical strength for the plants. And for the manufacture of alcohols, papers and carbohydrates acts as a raw material. So we have n number of applications like this. Therefore carbohydrate is one of the complex molecule present in a living system. That's why carbohydrate is the best example for biomolecule, and that is end of the first biomolecule, that is carbohydrates. Now I am going to talk about the second biomolecule, that is protein. Carbohydrates are the source of energy, whereas proteins are essential for growth of life. This is the main difference you need to know. We need proteins for the growth of cells. If you look over the chemical composition of proteins, of course we have carbon, hydrogen and oxygen, and one more very important element we have, that is nitrogen. So proteins are complex nitrogenous organic compounds essential for growth of life, that we call it as proteins. As we know, amino acids are building blocks of proteins. Amino acids join and we are going to get a complex structure, that we call it as protein. Remember, the main element present in protein is nitrogen. So now we'll see about amino acids. Amino acids. So what is actually the meaning of amino acids and the related concepts I am going to discuss here? We know that one. Amino acids are the building blocks of proteins. So with respect to chemical composition, I am going to talk about amino acids. Remember, in any organic group compound, if you have carboxyl group, and in any organic compound, if you have amino group, and that organic compound is nothing but amino acid. Carboxyl group, what is that? Bond COOH. Amino group, how we represent? Bond NH2. In simple language I can say, in organic compound, if you have a bond COOH and bond NH2, that is as good as carboxyl group as well as amino group. That organic compound we call it as amino acids. Then what would be the general structure, we'll see now. And before moving with that one, we'll see what actually the meaning of alpha amino acids. Alpha amino acids. As I mentioned already, let me consider this is a carbon. We have carboxylic group. We have a amino group NH2. There is a bond between carbon and nitrogen. And of course we have hydrogen, and here R will be the side group. In general I am going to draw. This is the structure of alpha amino acid. And now I will tell you why we call it as alpha amino acid. And now I hope we can say this is belongs to amino acids. Why? Because we have carboxyl group as well as amino group. Therefore, this organic compound is nothing but amino acid. And R is the side chain, as I mentioned. So if you consider this as the main functional group, that is carboxyl group, and the carbon which is attached to the functional group, and this carbon we call it as alpha carbon. I hope you know this concept. So this is alpha carbon. Why? Because this carbon is directly attached with the carboxyl group. And if you have one more carbon, that we call it as beta, gamma, delta, like that it continues. So the carbon which is directly attached with the functional group, we call it as alpha carbon. And one more, the very important group, that is amino group, that is alpha with respect to COOH. Therefore, this amino acid we call it as alpha amino acid. Amino group is attached with alpha carbon, and that is alpha with respect to COOH, and that organic compound we call it as alpha amino acids here. Try to know that one. Alpha carbon we have COOH as well as NH2 group here. So this is the general representation of alpha amino acid. Know that one. This is the general representation for alpha amino acid. Some examples we will see. Now I am going to talk about one very important example, that is the glycine. So glycine is well known amino acid. So now I am going to draw the structure of glycine. So carbon we have, and COOH group we have, and NH2 we have, and hydrogen we have here. So only the change is R. So R is going to be replaced by H, and that is the structure of glycine. Know that glycine belongs to alpha amino acid. We have carboxylic group and amino group, and we have H above and as well as below, and that is the representation for glycine. And remember, these amino acids can be represented using symbols also. And what is that symbol? GLY stands for glycine. So the first three alphabets if you consider, and that would be the symbol for representing amino acid. GLY, the first three alphabets, and that is nothing but the glycine. And one more example I am going to consider, that will be alanine, and the symbol I hope you can guess, that is ALA, alanine. So we will see what would be the structure of that one. Carbon we have, and COOH is one functional group, and one more is NH2, we have H, and if you replace R by methyl group, that is CH3, and that would be the structure of alanine. So this is glycine and this is alanine. So this is how we can give examples for amino acids. Basically, there are 20 alpha amino acids are known. We will discuss what are those later. So this is how I can explain the concept of amino acid and alpha amino acid. Remember that the two very important functional groups are carboxyl group and amino group, and these one NH2 group is alpha with respect to COOH, and that we call it as alpha amino acid, and this is the general representation for alpha amino acid, and the glycine is the example, and one more alanine I have discussed. So now we will see what are the different types of alpha amino acids. So now I am going to talk about the types of alpha amino acids. Types. So the first type is acidic alpha amino acid. The first one is acidic alpha amino acid. We have three actually. The second one is basic alpha amino acid, and the third one is a neutral amino acid. I repeat, we have three different types for alpha amino acid. The first one is acidic alpha amino acid, basic alpha amino acid, and neutral alpha amino acid. So we will see one by one what actually the basic alpha amino stands for, and acidic, and one more is the neutral. And before that, let me explain how actually the acidic nature we are going to observe and basic nature we are going to observe here. Since we have two functional groups, what is that? Carboxylic acid, and one more is NH2. Okay, so since we have bond COOH, so now look over just the bond COOH, and we know that one, according to Arrhenius concept of acid and bases, when any compound that produces H plus ions when dissolved in water, and that we call it as acidic in nature. So on ionization, after ionization we get a COO minus, and H plus we get here. For your reference I will write here, we are going to get COO minus and we are going to H plus after ionization. And because of that reason, and this is the main reason for acidic property of alpha amino acid. And why we have the basic nature in alpha amino acid, and the main reason is one more functional group. What is that? NH2. According to Lewis theory of acid and bases, on nitrogen we have two electrons, that we call it as one lone pair of electrons we have. Since we have a lone pair of electron on nitrogen, that is easily available for protonation, donation. So any compound which provides or donates lone pair of electron, we call it as Lewis space, isn't it? So because of this, the lone pair of electrons which are present on nitrogen, and the alpha amino acids have the basic property. So carboxyl group is reason for acidic nature and amino group is reason for basic nature. So after knowing this fundamental concept, we will see acidic alpha amino acid and basic alpha amino acid. So if we have 2COOH group and if we have one NH2 group, and that alpha amino acid we call it as acidic alpha amino acid. Very simple. I hope we can guess what would be the meaning. So we have 2COOH group and one NH2 group. Okay, and one can say that that kind of amino acid we call it as acidic alpha amino acid. Example I am going to write here: aspartic acid. Aspartic acid belongs to acidic alpha amino acid because in the structure of aspartic acid we have two COOH and one NH2 group. The second class is basic alpha amino acid. Basic alpha amino acid. And I hope you can guess, in this case we have one COOH whereas two NH2 groups we have. So two amino groups we have whereas only one carboxyl group we have, and that constitutes the basic nature of alpha amino acid, and that we call it as basic alpha amino acid. And the best example I can give for that is lysine. The third one is, as I mentioned, neutral amino acid. Neutral, it won't show acidic nature as well as basic nature, and I hope you can guess what would be the constant. So we have one COOH group and we have one NH2 group, and since one carboxyl group and one amino group we have, and that alpha amino acid we call it as neutral alpha amino acid. And the example I am going to write for that is the glycine. I have mentioned structure already. So we have only one NH2, we have only one COOH, and therefore the glycine belongs to the neutral alpha amino acid. This is how we classify the alpha amino acids based on acidic and basic nature, that is acidic alpha amino acids, basic alpha amino acid and neutral alpha amino acid. We have one more kind of classification, and that is, let me write here the name of that, that is essential alpha amino acid, and one more you can guess, non-essential alpha amino acid. Essential alpha amino acid and one more is non-essential alpha amino acid. So we will see what is the meaning of essential and non-essential amino acids. Self-explanatory word. Essential amino acid, that is required in the body for the growth of cells, as I mentioned. Non-essential amino acid, that is not required already. This is the basic meaning, but actually the meaning of essential amino acid is the alpha amino acids which are not synthesized in our body. So these essential amino acids, they are not synthesized in our body, but such kind of amino acids we need. Why? Because for growth of cells, isn't it? And what we have to do? We have to consume balanced diet. We have to consume good food so that those essential amino acids, they enter in our body and they help for the growth of cells. That's why I can say essential amino acids, they are not synthesized in our body but provided through diet, provided through balanced diet you can say, and that we call it as what actually the essential amino acid. Okay, for that one I am going to write here the keywords. They are not synthesized. They are not synthesized in our body, but they are provided through diet. They are provided through diet, and that we call it as essential alpha amino acid. And the example I can say, and the example for essential amino acid is the lysine. So how I can explain the function of lysine? Lysine is essential for our body, for the growth of our cells, but lysine cannot be synthesized inside our body. So if we take the balanced diet, and through diet that lysine amino acid is going to enter, and that functions for the essential for growth of life, and that we call it as what actually the essential alpha amino acid. Opposite of that, what is that? Non-essential alpha amino acid. So what is the meaning of non-essential alpha amino acid? You can guess, that is going to synthesize in our body. So the alpha amino acids that synthesize in our body naturally, and that we call it as essential amino acid. And the best example for that I can say that is the glycine. So glycine is the best example for that one. Remember, glycine is the best example for naturally occurring amino acid. Glycine synthesis in our body already, and that helps for the growth of our cells. Therefore glycine belongs to non-essential amino acid. Here don't get confused with essential as well as non-essential. Essential amino acid, they are not going to synthesize in our body, whereas the non-essential, they are going to synthesize in our body. Then what to do if amino acids are not synthesized in our body? We have to take that through balanced diet, and lysine belongs to essential, whereas the glycine belongs to non-essential amino acid. This is how amino acids can be classified into one more category, that is essential, and one more is non-essential alpha amino acids. After knowing the classification of amino acids, we'll talk about one property, that is Zwitter ion. So we'll see what actually the Zwitter ion stands for. So here I need the structure of alpha amino acid, and the structure is, see here, carbon we have COOH, and one more functional group is NH2, and H, and in general I will write R, and this is the alpha carbon, we know that one, and this part is the nature reason for acidic nature, and this bond NH2 is the reason for basic nature. So we'll explain what actually this Zwitter ion stands for. After ionization, what happens? We get a COO minus and H plus. So H plus we got here, and this H plus is gained by this NH2. So since we have a lone pair of electrons here, so there is shift of H plus from COOH to NH2. So what we are going to get? This is reversible actually. So we are going to get C double bond O minus, because H plus has been released, and here that proton is gained by this NH2, so we get NH3. So that has been gained one proton, so we get a positive charge on nitrogen. So we have hydrogen as it is above, and R the side group I am going to write. So this ion, and we call it as a Zwitter ion. So try to know that one, Zwitter ion, and this is how actually it is formed. So if you get a question, draw this Zwitter ion, and you need to draw this. So how actually this form I explained here. So what is the meaning of a Zwitter ion? In alpha amino acid, the carboxyl group loses proton, and that proton is gained by amino group to form dipolar ion. See, on oxygen we get minus, on nitrogen we get plus. So dipolar ion we get. So this dipolar ion formed, that we call it as a Zwitter ion. Draw the general structure of a Zwitter ion, and this is the general structure of a Zwitter ion. Sometimes in the examination we get, draw the structure of glycine Zwitter ion. See here. So now I am going to draw the structure of a glycine Zwitter ion. So how need to draw? See here, carbon we have, Zwitter ion means we have a COO minus, isn't it? And we have, what is that? NH3 plus, okay, and we have H. And I explained you already, in case of a glycine, the R is replaced by what is that H, and that is the glycine Zwitter ion. And if I ask you to write the alanine Zwitter ion, what you are supposed to do? R has to be replaced by what actually CH3, and if you write a CH3 in this place, and that would be what actually the alanine Zwitter ion. And this is in general, remember, in case of Zwitter ion we have dipolar structure, COO- and NH3+. So this is a general structure of Zwitter ion, whereas this is a general structure of alpha amino acid. Don't get confused. In case of Zwitter ion, we have dipolar structure. So that is the concept you need to remember, and that is the concept related to Zwitter ion. So now we'll see what about optical activity. Optical activity, optical property we'll see. So now what is the final statement? What I am going to consider is all alpha amino acids are optically active. Listen to the statement what I said. All alpha amino acids are optically active, and then you should know the reason behind that. Why these alpha amino acids are optically active? Because I mentioned this already. If a compound is optically active, that should have asymmetric carbon, isn't it? So all amino acids are optically active. That means all amino acids have asymmetric carbon except one. Do you know what is that one amino acid that is optically inactive? I hope you can guess. The glycine is the amino acid which is optically inactive. Okay, why it is that? For your reference, I am going to draw here. Glycine, carbon bond COH, and we have NH2, we have H here, we have H here. This is the alpha carbon, asymmetric carbon, carbon which is joined to 4 different atoms or groups, but this carbon we have hydrogen, we have same groups, identical groups. We don't have 4 different here. Therefore, this you cannot represent by asterisk or star. So this is not the asymmetric carbon. So since glycine does not contain asymmetric carbon, glycine is optically inactive, I can say. So the final statement what I am going to say here is all alpha amino acids are optically active except glycine. The reason behind that is glycine does not contain asymmetric carbon. And one more statement you try to remember, the glycine is the only alpha amino acid which is naturally occurring, which is optically inactive. So the glycine, the best statement what I can say is glycine is naturally occurring, optically inactive alpha amino acid. I repeat, naturally occurring, optically inactive alpha amino acid. How it is naturally occurring? As I mentioned, glycine is the best example for non-essential, synthesized in our body already. So therefore, glycine is the best example for naturally occurring, optically inactive amino acid, and that is about the concepts related to optical activity. Remember that all alpha amino acids are optically active except glycine.